continue with the group molecular table and other things. I was telling one section we have just missed it. So that is systematic determination of systematic method to find out the point group for a given molecule. Okay, so shall we just do that? Okay, so for any given molecule, you can find out a point group. So basically, you have to check. There's a flow chart. So this is just a flow chart. So check for a special group. So answer is yes. Then you split into branching. So in that you check for whether the molecule is linear. If it is yes, or you can say here you can say it's you can say yes. Then that could be two things. One could be C infinity V or D infinity H. Okay, and if the molecule is linear, and check for whether I is present. The inverse infinity is present. If it is so, yes, then you get D infinity H. Okay, if the molecule doesn't have I symmetry, then this is called as C infinity V. Okay, so this is way. I mean, the molecule is linear, and then it has I. Then you call it as D infinity H. The molecule is linear and it doesn't have I. So here, no. Answer is no. Okay. So what are we writing? Left answer is no. So that is C infinity V. Here, if the molecule is non-linear, I just say yeah. So possible point groups are tetrahedral, octahedral, and icosahedral, which we used to. I mean, we call it as a special groups. So only these three possibilities are there. If it is non-linear and they are special group, and these are the possibilities. Let's talk about other groups. If the answer is no, it is not special group, then what? Now you can find out various groups. Let me take my notes. If the molecule has CN symmetry, okay, so you have to check whether the molecule has CN symmetry. If it is yes, then you can say search for whether the molecule has n times of C2 perpendicular to Cn. So this is present. If answer is yes, okay. So I think we have seen the what does it mean by n times of C2 perpendicular to Cn. If the molecule has this property, then answer is yes. Then again check more. If the molecule has sigma H, I'll just write it here. If the answer is yes, then it will be D groups. So it is D, N, H, right? And if the answer is no here, if the molecule is Cn and then it has n times of C2 perpendicular to Cn, yes, then it doesn't have the sigma H, then it could be D group, but it could be Dn or DND. That's it. So here again, how to differentiate DND and Dn? You check for sigma D plane. If it is yes, then this is DND. If the answer is no, then you call it as Dn. Okay, so this is the way of finding out point group, and we left here, right? The molecule has Cn property, and then we said yes, whether it has n times of C2 particular to Cn. We have put a question mark. If the answer is yes, then all the D groups. If the answer is no here, then the branch comes like this. Yeah, so then now we have to check for what? Sigma H. If it doesn't have, you check for sigma H. Check for sigma H here. The molecule has sigma H or not. If the answer is yes, then you call it as CNH. Something similar, what we do it in D. Same way, you have to check for sigma H. The answer is no. The molecule doesn't have sigma H. Then you can say it is CNV. The molecule will have CNV. You can check for sigma V. Answer is yes. Then CNV. The answer is no. Then you call it as just Cn. Okay. I hope the last line is visible. Cn, Cn, CNV. So you want me to repeat? So Cn you have to check. Yes. Then if the molecule has n times of C2 equal to Cn, answer is yes. Then check for sigma H. If the answer is yes, then the molecule has a point group DNH. Here, if the molecule doesn't have a sigma H plane, then check for sigma D. If it is yes, then you call it as DND. If the answer is no here, sigma D doesn't have, then the molecule has DN point group. In this state, if the molecule doesn't have n times of C2 compared to Cn, answer is no. Then check for sigma H. If it is yes, then CNH. If it doesn't have sigma H, then you check for sigma V. The answer is yes, then it results in CNV. If it doesn't have a sigma V plane, then the molecule has just Cn. Because Cn is present here, we have said yes, so it comes Cn only. Okay. Now this part is there, but we have just left out this branch. So what is this branch? If the answer is no here, if the molecule doesn't have Cn, there is no rotational axis of symmetry. If the answer is no, then what it can have? Just check for sigma H. So check for sigma H. Okay. And the answer is yes. The answer is yes. Then the molecule has CS symmetry. Okay, so it doesn't have C2 or C3, C4 or C6, but you check for sigma H. If it is having, then it is called as CS. If it is not having sigma H, so answer is no. Then check for I. I can say I write it here. Check for I. The answer is yes. Then we can write CI. The point group is CI. If the answer is again here no, if the molecule doesn't have Cn symmetry, doesn't have sigma H, doesn't have I, these are not special groups, so nothing is there, then we call it as C1. I think this is a flow chart to find out systematically the point group for a given molecule. Okay, you start with the molecule here. Any molecule, check for like this, then you can find out. Okay, it's visible. I think I can go to the next topic if you are fine with this. I'll make it full screen. Okay, so shall I go to the next topic?
Yes, sir. Yes, sir.
Oh, so I'm erasing it. I think it is clear. I think so. We have covered one by one. If you see last two classes, if you remember, every point group we have addressed with some examples, right? We took a special. We talked about D infinity H, D, C infinity V, and then these groups C1, CI, CS. Then we talked about Cn followed by n times of C2 bound to Cn, and those are called D groups. So it will be DNH, DND, and DN. And if this property is not there, then we call it as CNH, CNV, or CN. You should have seen the examples. So any book, group theory book you choose, this one also. So for each point group, have seen the examples. So any book, group theory book you choose, you will find this systematic way of this flowchart. You will find which you can use it. Okay, so now let's come back to the group multiplication table. Yes, so last class we talked about C2B, right? We have done for C2B. I gave it for C3. Anyone tried? Group multiplication table. Can you please repeat? Someone said something. Robin? Robin was replying?
Yes, sir.
Yeah, so anyone done this? You have done this C3B group multiplication table?
Yes, sir, I've done that.
You have done it.
Yes, sir.
Okay. So you are sitting in front of it, or you are having that?
Yes, sir, I'm having that in my notebook.
Okay, tell me what is multiply Z. What do you get?
Sigma V dash into sigma V double dash. Sigma V dash. Sigma V double dash. We'll get C3 2.
C3?
2.
C3 2.
Yes, sir.
Let me check. Sigma V and sigma V double dash. Okay, correct. C3 2. So everyone, thank you, Robin. So what about others? Everyone done it? Huh?
Yes, sir.
Yeah, repeat please. Okay, I'll ask with my student. Nidhi, if you have done it now, you show the paper, switch on your camera, just show the paper to the screen, something like this. I'll show you my answer. Something like this, you display it. Nidhi, you have done it?
I have to find it. Like,
You have to find it. So,
yes, give
who
me.
is having in front of them? They can switch on the camera and just display like this. Anyone, I'll just pick the name. I'll just going to call. Okay. Who will we call? Yes. Yeah. Let's start with the class rep. Naina Goel. You have done it?
No, sir. Actually, I didn't understand this group multiplication table.
Okay. Yeah, I'm expecting some answer. Yes, yeah. So something should be known, right? Yes. Naina, okay, fine, not a problem. We'll redo it. Okay, C2V
Yes,
will redo it. What about others? Let me see. Akansha,
Yes, sir.
you have done it?
No, sir.
Did you understand or not?
Sir, I'm actually very new to this subject. I'm
Okay.
learning.
Okay, but I did it for C2V, na? Last class
Yes.
I did it. Anyway, fine, we'll do it. Anyone, maybe Ritik Bansal?
No, sir.
No, sir. Okay. Maybe I'll again do it for C2V. Those who have done it, excuse me, you please work it out for C2V, but I'm going to again redo for C2V, okay? C3 I'm
I
not going
found it.
Huh?
So I found it. Should I show you?
Yeah, who has done it, you can display it. Yes.
So Nidhi here. Yeah.
You're saying something.
Sir, I have that table in my notebook. Can I show it?
Okay, where is your notebook? Anyway, I'm not getting the reply, so some people
Is
do
it
not.
visible, sir?
Tell
Sir,
me.
is it visible, sir?
I think no. Your Jihad, huh? Jihad.
Yes, sir.
No.
Yes, yes, ulta aa raha hai, but not bad. Yes, yeah, visible. So you have done for C3. Yeah?
Yes, sir.
Good. So yeah, partially visible. It's good. I think you have attempted it. It's very good. Yes. Yes. So
Thank you, sir.
thank you, Jihad. Yes, fine. I'll pin up to mine. Okay, so yeah, those who have done it, yes, it's good. Let me, for those who are having problem or those who have not attempted it, let's redo for one more time. I'll leave it to you, C3V, okay, because it takes a long time. So I'll just do it for only C2V. So I label this molecule as say H1, H2, atoms H1 and H2. So axis will define as XYZ. Okay, so this is X. I call this one as Y, and this one as Z. Okay. So water has three symmetry operations, right? Water has three symmetry operations. That point group is C2V. One is E, other is C2, which is going to rotate in the Z axis. So through this axis, we are going to rotate 180 degrees so that it will result in other symmetrical structure will result. And then what we have sigma V plane. We call it as sigma V. Let's consider this as one plane. Yeah, the one which is on the board. The water molecule is placed on this board. That means we are placing a mirror on top of it. So on sigma V XZ plane, XZ plane. Okay. So X is right side, Z is Y axis. I mean the vertical axis, which is both on the plane. So this is one plane. So I call that as X. And there is another symmetry operation, right? This is sigma V. So you cut the molecule in two. You place the mirror, cutting the this molecule into half. Okay. So what happens? This H will be mirror image of this H. So that axis is called as sigma V. We call it as prime, and we are cutting like this. This is Y and Z. Because Y is coming out of this board and Z is vertical, going up. So if you place a mirror something like this, which will break this this molecule into half. So I call this as sigma V prime YZ. V prime YZ. Okay, so I write this one in both slides, in both row and column. C2Z sigma v xz, sigma v prime yz. Okay, so let's start with each operation. So E is very simple. I mean, first row and first column is going to be very simple because you're going to multiply with the E. So first row, let's finish. So basically, this is a row into column. You have to multiply. Okay. So for the E and E to perform, it is E. And C2 multiplied by E, it is again C2Z. So what we are actually doing is, I'll erase this. So we are performing mathematical. You can say it's an operation. So it's a symmetry operation. So E what? E multiplied by C2. So this is what we are doing. We generally in symmetry operations we go from right to left. Okay. So say this is I call it as a function F. F is a molecule. So you place the molecule here, and then perform E operation and perform C2 operation. So you have to write what you are going to do. That's what we are doing. So F is a water molecule here. Okay. So I just write C2 into E water. So what you are going to get. So that's what we are just find out. So E into E. If you perform E on water, it's not going to change anything. And again, if you perform C2, it's basically it's not going to change. So just you will end up with C2 only. So it will result in C2. C2 of water you get. So that's what I have written here. Again, similarly, if you perform sigma V into E, it will result in sigma V of Xe. Okay, and E. So whenever you multiply with identity, it's not going to change anything. The same element you get. So first row and first column, you will get what you have on its column and row. Okay, so because identity element is you're not as such doing nothing, so it just comes like this. Now let's go to the second row, second column. So if you perform this, so if you have to multiply with C2 into C2. So what we are doing is C2, two C2s we have to perform. So as I said, the direction is from this to this. So first let's start with this C2. Okay. So water molecule you take. Evaluate these things. I made it as 1, 2. Perform C2. To perform C2, what happens? So this H will go to this side, right? The H will be interchanging its position. This is first H2. Then again, you perform second C2. So this is done. Now you perform second C2 operation for this molecule. Again, C2 is present here. Rotate it by 180 degrees. Now what happens? You get back. This first time it is H1, H2, then it becomes H2, H1. Perform again C2. This will begin again, it just rotates. So it becomes H1 and H2. So this is nothing but the starting one, right? So this is as such, you're performing E operation. Yeah, so if you start from water, H1 right side, H2 left side, if you perform E, you will end up with the same. So that's what we are writing. This element, C2 into C2 will give E. Yeah, so in this water molecule, if you perform, all the diagonal elements will be E. Sigma V into sigma V, again it will be E. You can check it. Yeah, so again here you can see, if you play sigma V plane. So I play a sigma V plane of Xz. In this, so if you place it on this molecule, nothing going to change. So the H2 will remain there, H1 will remain there. So this is sigma V, we have done it. There is another sigma V, right? There is another sigma V we are going to perform of Xz. So if you perform again, you are going to place the mirror on top of it, nothing is going to change. So it is as such E. So we can see starting and the end has E only. You have the same structure, so you call it as E. Similarly, you can do it for sigma V prime, and sigma V prime will result in E. Now let's try with sigma V multiplied by C2. So we have to find out this. Yeah. So first start with the sigma V multiplied by C2. Okay. So this is what I'm going to do. So sigma V is, as I said, you have to start from the right side, come to the left side. So sigma V is, if you perform, it's not going to change. The molecules same atoms are going to be in the same position. So that is sigma V. And now C2 if you perform to this molecule. So C2 is here. You rotate by C2. So if you rotate it, what happens? So this will be 2 comes here, H1 comes here. So this is the end structure where hydrogen 2 is the right side, hydrogen 1 is the left side. How do you reach this structure from the starting? So that is how do we do that? So that you can get it by C2 operation. So C2, there is one way, or you can place a mirror. You can place a sigma V prime mirror, which is on Y Z. Place a mirror here across this molecule, then this atoms will be interchanging. So we'll end up with sigma V YZ. Okay, so that's what here it is. So sigma V multiplied by C2 will result in sigma V prime YZ. Okay. And similarly, one can check for sigma V prime and C2. So one way, easier way is you can fill it here. But anyway, we can work it out. So we are just going to take.
Sir,
Yeah.
sir, why we have not written C2 here?
Okay.
We can,
Yeah, that's a good question. Why we are not writing C2 here, right? You can say you can C2 also give the same one. But if you see the row, already C2 is present here. Okay. So in each row or in each column, then the element should be unique. It cannot repeat. So for that reason, C2 has not been written.
okay, sir.
Okay, so that's the reason. Yeah. So I think you must be following the Japanese game, right? The board game, the Sudoku, right? They have 9 boxes. In that, you have to fill the numbers 1 to 9. Am I correct? Yes, I think you might have seen
Yes, sir.
newspapers or in magazines. You'll find the same way. I mean, it has to be unique. 9 numbers you have to fill it 1 to 9. It cannot be repeating. So something similar in this table. You have to fill it, and the elements should not be repeating, either in this row or column wise. That's why instead of writing C2, we wrote sigma V. Let's do this one and we wind up. So this is sigma V prime multiplied by C2. Sigma V prime and C2. That's what we want to find out. So let's try with sigma V prime, which is YZ axis. So basically, you're cutting the molecule into 2. So what happens? H1 comes here, H2 goes there. For that, then after that, sigma V is done, then C2 will perform. C2 again, if you perform, you will end up with H1, H2. Okay, so how do you reach here? From here to here? One is already E is taken in this. If you see E is already taken, C2 is taken, sigma V prime is taken. So only way is sigma V, which is XZ. Yeah, sigma V will perform. Sigma V is placing the mirror on this board, so the atoms will be as such will be remaining. So because this is equivalent to sigma V. That's what I just want to write. Okay, so this way you can fill it, and yeah, so I can write here. So sigma V into sigma V we have written. There are 2 phases here. What you will get? So C2 is already there, E is already there. It could be sigma V prime. I guess so. Because sigma V is already there. So you will get sigma v prime, and this is yz. Okay, and the remaining one here is C2. C2 is, yeah, you can see it's all unique. That's why you can fill it. You can verify, yeah. You need to verify at least once what I'm writing here. So last row, we have again two entries not filled. To C, sigma prime and E is already taken. And here sigma is B prime is already there. So it should be sigma B. Sigma V of xz you will get. And then again, sigma V into sigma V prime. What is missing is C2 is missing. Okay, so you can see every row or every column, it's all unique. All four elements will be there. So like this, if you fill it few, you can fill the remaining one by just seeing the what is present and what is not present. Okay. So is it clear?
Excuse me, sir. Excuse me, sir.
Yes, please.
Yeah, sir, there is a confusion between sigma yz and C2. So we can use the concept of phase here, sir. Like in C2, the front side of one molecules get replaced by a back side of the other. But in sigma yz, the phase, like the front phase remains the same. So we can use that to distinguish both, na?
Sigma yz, we are putting,
Yes, sir.
we
So
are
the
putting a mirror here. Oxygen is there, only H is interchanging.
yes, sir. The like we are considering hydrogen as sphere. So the
Yes.
front face of H1 will be replaced by front face of H2 face. But in C2, the front face of H1 will replace by back face of H2. So like that we can
Okay, I agree,
distinguish.
but hydrogen is a sphere, no? Spherical.
Yes, sir. But I'm just to like not to get confused, like Nana asked why are we not using C2 at the place
Yes,
of
okay.
CYZ. That's why like
I agree. Like sometimes you can take the orbitals also. These are all, we'll come to that. Here we are taking atoms as in a spherical shape.
yes,
Okay.
sir, yes.
So considering each
Okay.
atom as spherical, based on that we are getting this. But say when you study benzene, no, C6H6, we don't consider
Yes,
atoms
sir.
as spherical, but we take orbital shapes. So
Yes,
in
sir, yes.
benzene, there are pi orbitals, right? Px, py, pz. So
Yes.
at that point, we have to see what representation we are taking. If we are
Yes.
taking uh, px orbital, so it will be say px will be like this, and py or pz will be like this, and py will be like this. So, the concept which we applied here, considering the atoms are sphere, the same cannot be applied when we are taking orbital shapes, p orbitals or d orbitals. So first we decide what is the representation, whether we have to consider the atoms as a sphere or we have to consider that as a orbital shapes, and then you apply for the these operations. Okay, that's what I think she was mentioning. We'll come to that, but at present we are considering atoms as spheres. With that, we have just built this molecule. Oxygen also we are considering as a sphere. Okay, just one atom, one sphere, not as px or other orbitals. So if you consider px, like if you consider this as orbital, then of course there will be changes. But we are not considering as orbital; we are just considering as a sphere. Then we can draw like this. Okay, so now you please work it out. C3V, ammonia is the best example. H, and there is a pi lone pair. So it's all symmetric. So you consider this as all spheres. All atoms are spheres, and then work it out for C3V. Okay. Any other question in this? So this is very important property because when we build up character table, so this becomes very handy. This multiplication table, that's why we are spending a lot of time for this. The next class on Monday, I think, right? I'll ask every one of you to display what you have worked out, or you send it by email before the class. Okay.
Sir, can I ask a question?
Yes.
Yes, sir. Why we are doing this?
Why we are doing this? So with this multiplying table, we develop what is called as a character table.
Okay, sir.
Okay. So character table is you will have various parts of a character table. If you have seen a or quantum chemistry book itself, like Macquarie or any other book, to see at the end of the book, before the index, before the bibliography, you'll find various tables of point groups. For each point group, there will be what is called as character table. It's called as character table. There will be a point group, and all the symmetry elements will be there. And there will be two more columns. At least in the quantum chemistry book, you will find two columns. Here, all numbers will be there. So for C2B, it will be A1, A2, B1, B2, and there will be numbers here, something like this. So, and here you will have some properties like X, Y, Z, Rx. Sometimes Y and Z will be at the same place, Rx, Ry. So you will find table something like this. So to build this table, we need multiplication table, group multiplication table. We'll arrive at this stage. Why we need this is these two columns are very important. It will tell whether the peak is, the molecule undergoing excitation by absorption of light will result in will give a signal or not. So only when the molecule give a signal for IR radiation or rotational transitions, only when it vibrates in, for IR it has to vibrate, right? So only it vibrates in x-axis. If it is vibrating in different axes, then it will not give signal. So if it is, so and again similarly, this last column is for rotational transitions. Microwave spectrum one can predict. For this column, it is for IR and Raman, and this column is for microwave spectrum. So based on the orientation, you can predict whether the vibration will give a signal or not, and if it is vibrating, in which property it has. So A1 is highly symmetric. I will come to that. All these things, and these are less symmetric elements. Okay, so to build this table, character table, we need to have a group multiplication table. So that's the reason. So now we just simply wrote for C2B, right? We wrote it in by just drawing the molecule. Next step is we use a matrix form, and then write the group multiplication table, and then finally we'll come up to this character table, which finally will connect to the spectroscopy. So that's the logic. It will take some more time to reach that stage. Okay, so we are just building the basics before building this, before coming to this character table. So I hope I answered it partially. So let's go for next topic. So there's something called operator. We started, right, like algebra of linear operators. You might have heard about this. At least there are four. Maybe you remember, it is called additive. The algebra, the linear operators have, I don't want to say additive, or it's called a sum law. So again, this product law. then associative and distributive. So sum law is, yeah, if you have two operations, I call it as phi1 or O2. Sum it up, you have a function, then it will result in 1f plus O2f. You can write like this, right? If you have sum law means it's all operators, these are basically operators. So if you have a function, you can either sum it up and then act on a function to give the answer. That will be same as if you individually perform it. Product law is also same thing, similar. Yep, will do the same. So if you perform together or if you do it individually, so this is product law. Similarly, one can write for associative law. The same as O1, O2, O3. So I can see these are all operators. The distributive is I'm sure you have studied these things in school, maybe in 7th or 8th standard. So this can be written as O2 plus O1, O3. So this is all linear operators, but for symmetry operator, which you are studying now, right? So symmetry operators also obey these laws. We mostly use, most of the time we use this product law and associative law. Okay. So all the symmetry operators obey these laws. So for example, if you take for even for C2V, which we considered, just take one or two examples, then we go to the what is called as groups. So say C2 sigma V prime we have, right? So if you take C2 and sigma V, take the product something like this, and then if you invert it, say sigma V multiplied by C2, you'll get what? This will be, as per the definition, it says same. So what you will get? To perform C2 and sigma V, from the group multiplication table, you can say what is the answer. You get sigma V
prime.
Yeah, so if you perform sigma V into C2, so basically we have to perform in this direction, reverse sigma V multiplied by C2. So it will result in sigma V prime. And if you just invert it, sigma V multiplied C2. So again you perform this operation. C2 you perform and then you perform sigma V. This will also result in sigma V prime. Okay, so this is as similar to linear operators. Even the symmetry operators also have this property. So this is one of the property, and similarly you can have it for associative property also. If you take product of 3 instead of just 2, you take product of 3. For example, C2 sigma V prime. This will be equal to you will end up with C2 and then perform C2. So if you perform sigma V prime and sigma V, this is C2. So C2 into C2 will result in E. So this is left hand side, and if you start with C2 sigma V prime. Now you perform sigma V into C2. So that was coming at sigma V prime. Again multiply with sigma V prime. So it will result in E. So you can see if you perform these two operations first, and then act on C2, you will get E. If you perform first two, C2 and sigma V, and then act, you get sigma V. And then if you perform sigma V prime, that again results in E. So this just associative law holds good. So like this, one can prove all other laws. Generally, this is valid. You try for any other combination, you will resolve this one. Okay. 47. Shall I start what is called as? Maybe I'll just give a definition, then we'll see the properties. Okay. So I just want to say this symmetry operators also obey the operator algebra. So we'll see what is called as a group. So group is nothing but the collection of elements satisfying 4 characteristics. Collection of group is a collection of characteristics. So collection of elements means which satisfy 4 characteristics. So collection of, in water molecule, which has a point group C2B, it has 4, right? I mean, there are 4 symmetry elements or operations, you can say. Similarly, a collection of elements is called as a group. So all these 4 elements in water molecule, E, C2, sigma V prime, all are called as all combined. It's called as a group. It forms a group. Similarly, for C3V, for C3V you have E, C3, C32, sigma V, I call it sigma V prime, sigma V double prime, sigma V triple prime. So C3V has these symmetry elements. So all 6 are called as a group. Okay, so this is a collection of symmetry elements called as a group, and all these 6 will satisfy some characteristics. It has some 4 characteristics. What are they? You just see maybe next class. Okay, I'll just stop it here, or I can quickly tell. Like, no, it will take some time. The group is a collection of elements which satisfy 4 characteristics. Each is one is basically if you combine two elements, it will give a third element. For example, in water, C2 sigma V prime, right? So if you combine these 2, it will give another element which will be part of the group. So that is first characteristics. Second characteristic is one element in the group must always commute with each other. The example is identity. Identity commutes with every other element in the group. So that is another characteristics. Third one is third is what? The associative law must hold good. So basically, if you combine these 3, you will get some answer, right? So again, if you combine other way, like I can say AB into C will be equivalent to A into BC. So that is associative law should hold good. And fourth property is each element in the group will have its inverse. The inverse means what I mean is a reciprocal of each other. So basically here, if you have C2 means it has C3. I mean it has C2 inverse. The fourth one is if we have C2, then in a group C2 minus 1 is also existing. And if it is sigma V is present, sigma V minus 1 is also there. That's what it means. The inverse also exists. Again, sigma v prime is there. Its corresponding sigma v minus prime is also there. So whatever you perform that operation, you just inverse it to get back to the original. So that is inverse we call. So these four properties each group has. Then only we call it as a group. So it's basically a collection of elements which satisfy four characteristics. What are they? I said first one is combination of any two elements will give another element which is part of that group. So again, there is an identity element which commutes with. There is a one element which commutes with every other element in the group. So that is identity is present. Third is associative law must hold group. Fourth is every element has its own inverse or reciprocal property is there. So these are the four characteristics for this group. We'll take an example for each case and then explain it. And then we also study what is called as abelian group. And then we study what is called as a order of the group. Okay, so from that we'll build it up. And after that we study what is called as a subgroups. After that we go for class. Okay, so these are the terms, new terms you'll see. But our ultimate aim is to predict the IR spectrum or Raman spectrum or rotational spectroscopy, and also ligand field theory. I mean, a little bit of metal ligand coordination, what symmetry has to be there, which orbitals are involved. So those also we'll see. So to analyze that, we need all these background. So that's the plan. Okay. Okay, I'll stop it here. Monday we'll meet. Yes, yeah. Any question?
Sir? Hello, sir?
Yes.
Sir, do we have to mail you that group multiplication table of C3 point group before the next class?
Yes, you can mail. Yes, yeah.
Okay, sir.
Okay.
Hello, sir.
Yes, yeah. You please first understand. I mean, there is no hurry. If those who have exams, don't worry. But those who could do it, you just work it out and then send it.